So anytime you think that arrowhead points this way down this axis, that has to be shown that way. So I'm going to show all of those in tension. This guy's name is EF. This guy's name is EC. This guy's name is BC. They have all been guessed as tension. Alright. This free body could be used just like the other one was to solve for the force in member BC. The procedure would be as follows. Who are you looking for? BC. Cover it up so you can't see it. Who's left? Those are the guys you hate. I hate EF and I hate EC. Follow them until they meet at a point. There's where they meet. Point E. You say, well, point E is outside the free body. This piece of steel should not roll about any point outside the free body, just like it shouldn't be rolling about any point inside the free body. Perfectly legal to some moments about point E to solve for BC. Now, I told you I was really looking now for EF. Who are you looking for? EF. Cover it up. Who do you hate? EC and BC. How do you get rid of them? You follow EC and BC until they meet at a point. They meet at point C. If you will some moments about C, you'll cancel both of those unknowns out, and all you'll have left is EF. Now you'll have to be a little careful with EF, because EF isn't going to have a nice moment arm. In order to get EF, you'll have to show EF horizontal. Go ahead and break it up into two pieces. And EF vertical. When you do that, throw away the original EF and some moments about C. You'll notice that's pretty nifty. EF vertical goes through C. All you have left is EF horizontal. Knowing EF horizontal, you can turn it into EF, because EF times the cosine of this angle has to be EF horizontal. You can work backwards to get EF. Sometimes these two won't both go through, or one of them won't go through your point, and they'll both be left hanging out in your moment equation. Then get rid of one of them by saying that EF horizontal is to 5 as EF vertical is to 7.5. See, that'll let you substitute this in here if you wanted to. Notice where I got that from. This member moves to the left 5, and it moves down 7.5. Oops, I'm sorry. It moves 7.5 total. That's half of 7.5. EF horizontal moves to the left 5. When it moves down, half of 7.5. And therefore, EF horizontal is to the horizontal dimension as the vertical component is to the vertical drop. Alright. Now then, let's try one a little more like, probably a little more like they'd have. That one's a little complex, got a few too many loads. They're probably not going to put a whole pot full of loads on them, because if you can do one load, you can do any of them. Let's say that I have been asked to solve for the force in member IC. If you will notice, it comes, you can go ahead and try and solve for it. There's 3 unknowns. Usually you can't. But in this case, since it is perpendicular to a pair of members that are pure horizontal and have no vertical component, that's what they call a zero force member. And that doesn't mean that it'll always have zero force. When this 30 kip truck gets somewhere else, it may have some force in it, but right now it's not necessary. This is a zero force member. The force in this one is 30K. This is a zero force member. This is a zero force member. They may be there for nothing more than to brace these long members, but there's no real load in them. Alright, now, to solve for the force in member IJ, to solve for the force in member IJ, you must cut member IJ. Then, cutting as few members as possible, you would come on down like this, circle either end of the structure, and that would be your free body. In order to get a free body, you would have a member with an assumed direction on the force. You would call it IJ. You would have a member. It would have a force assumed. If you just always assume they're all tension, you can't hardly go wrong. Then if you get a minus, you know they're compression. His name is CJ. And finally, you have a member CD. Now, I'll assume that you've already solved for these reactions. If you are asked to solve for IJ, cover it up. Who do you hate? CJ and CD. Follow them until they meet at a point. If you will sum moments about point C, IJ will be the only unknown. This force times its moment arm. This force goes through the point. This force times his moment arm. And IJ times that same moment arm is equal to 0. I can use the same free body to solve for CD. If you want CD, cover it up. Who do you hate? I hate IJ and CJ. Follow them until they meet at a point. They meet at point J. Some moments about point J and they will drop out of the equations. Can immediately pick up and get CD. Finally, let's solve for CJ. Who do you want? I want CJ. Who do you hate? I hate IJ and I hate CD. Follow them until they meet at a point. Uh-oh. Being parallel, they'll never meet at a point. Therefore, anytime the two members you're trying to get rid of are parallel, you got a really easy job of it. Just don't talk about going in that direction. Don't sum forces horizontal. What you do is you get to drop back to one of your easy equations. Sum forces vertical or sum forces horizontal. For heaven's sakes, don't sum forces horizontal. Yes, you already know that. Yes, you already know that. They may both be wrong. Don't sum forces horizontal and let them get in your equation. Sum forces vertical, then both of them will drop out of the equation. All right. All right. Now, as opposed to trusses in carried loads with an item called a beam, beam have loads on them just like a truss does. Trusses are always loaded only at their joints. The members are too slender to take any loads except at those joints. Beam can accept a distributed load. Now the way you solve these kind of problems, well, this is kind of cute. Got two rollers, and that, of course, it doesn't have any horizontal force, but you probably come back tomorrow and somebody will have stolen it. So probably ought to make one of these at least a pin, and then have the other one be a roller. The way you do these is you break these things up into pieces you understand. For instance, I understand a rectangle. I don't quite know where the centroid of a trapezoid is, so I just turn it into a triangle and a rectangle. And you might as well take the whole rectangle all at once. There's no reason. You can split it up if it suits your eye better. You can break it up into a 100 pound per foot load, 4 feet over. It's a rectangle, so the centroid is in the middle. Here's 100 pounds per foot, because we're just going to continue that across, at 1.5 feet for his centroid. The centroid of a triangle is 1/3 of the distance from the fat end of the triangle, and this is now 200 pounds per foot. The reason being, we've already accounted for the 100 pound per foot as a rectangle. And you'd have to be careful to notice this one's pointing up, so it will be pulling up. Here's the centroid of that triangle. It is 1/3 of the base from the fat end. Now, let's talk about how much load we can put on this beam. The 100 pounds per foot times 4 foot gives us a number. 100 pounds per foot times 4 foot, feet cancels feet, that's 400 pounds, and it goes right in the middle. The 100 pounds per foot times 3 foot, that's base times height, is the area of a rectangle, is 300 pounds, and it goes right in the middle, 300 pounds. The area of a triangle is 1/2 base height. So for how much load is under this figure, we'll take 1/2 of 200 times 3. Half of 200 is 100. 100 times 3 is 300 pounds. So there's another 300 pounds. Pretty close to the previous one. This distance right here would be 1/3 of 3 feet, so that's 1 foot. This one is in the middle of that 3 foot piece, and so it is 1.5 feet over, so that would be 0.5 feet. Here's the reaction. We've already used up 1.5 feet, so this is 1.5 feet in here. This one is 2 feet since it's in the middle. Here's this reaction on this end, and here's the triangle load, and it goes right about there. Its magnitude is base times height cut in half. That's 2 times 3, that's 600 pounds. And its location is, now since that's 1/3 of the base, this is 2/3 of the base, 2/3 of 4 feet. So that's 8/3 of a foot. Whatever that comes out. What's left over here is 1/3 of 4 plus 2, that goes right in here. 1/3 of 4 is 4/3 plus 2. Give me a decimal on that.
3.33.
Thank you. 3.33 feet. Probably better to put all this stuff in decimal form. This is the reaction at some point vertical. This is the reaction at some point vertical. You solve this problem by summing moments about point A equal to 0. That's your most powerful equation. It allows you to get rid of one of your unknowns by picking that as your point of summing moments. And then it's just like we did before. 300 times his moment arm, 300 times his moment arm, those are positive. 400 times his moment arm, negative. 600 times his moment arm, negative. RB vertical times his moment arm, positive. Set them equal to 0 and solve for this. then you can sum forces in the vertical direction is equal to 0 would be equal to minus 300 minus 300 minus so and so and so and so, plus the reaction at A vertical plus the reaction at B vertical. Alright. Now, sometimes you'll have a concentrated moment on the beam, and that's handled a little differently. I think I'm just going to go ahead and make the free body out of this one itself. That's the reaction at C vertical. That's the potential reaction at C horizontal. It'll be 0 since nobody is pushing horizontally on it. And I'm going to replace this with a single concentrated load. 100 is its height, 0.4 is the base, and 0.4 of 100, that's 40 newtons of force. And now this thing here is gone. That's 0.2 meters and 0.2 meters. Listen, just like all the rest, just need to make sure you know what to do at this moment here. I need a reaction here also, reaction at A vertical. Since it's a pin, one force only. Sum moments about A equals 0 is equal to plus 100 newtons times his moment arm, 1/10 of a meter, minus 40 newtons times his moment arm, 5, 6, 7, 8, 9, 0.9 of a meter, plus the unknown RC vertical times his moment arm, 5, 6, 7, 8, 9, 10, 11, 1.1 meters. Now we've taken care of this. We've taken care of this because he has no moment arm. We've taken care of this. This guy here goes right through that point and has no moment arm. And we've taken care of this. This is our only guy left right here. Minus 2.5 Newton meters. It's not multiplied times the moment arm, no matter where the moment is applied on the beam. The reason is, the 100 Newton guy needed 1/10 of a meter to make a moment. The 40 Newton guy needed 9/10 of a meter to make a moment. He had to have a Newton times a meter, a Newton times a meter. This guy doesn't need anybody to multiply him. He was born a moment. He was born a Newton meter. When you stuck him on there, he was a moment. Therefore, if you actually multiplied him times a moment arm, you'd get something called a Newton meter squared. Nobody knows what that is. So anytime you see a concentrated moment on your free body, just plug it in your moment equation. When you sum forces vertical, here are your sum forces vertical. Minus 100 plus RA vertical. Minus 40 plus RC vertical. And that's it. You do not have anything up and down due to the 2.5. Because it doesn't go up and down. It goes round and round. Alright. The last thing we'll do are frames. Frames are pieces of steel. Unlike a truss never has a load in the middle of the member. It'd collapse immediately. The members are not strong enough in bending to resist that. So rather than being a nice slender piece of steel here, this is probably a 2x4 or something like that. You'll also notice member ABC is all one piece of steel with a pin at B. And member CDE is all one piece of steel with a pin at D. That means member AC is loaded in the middle of the member. That makes this not a truss. It is a frame. Now you can solve for these outside reactions many times by your equations of statics. Here's a pin. You'll notice that I put an AX force and an AY force, because every pin can have two forces. I also have an E vertical force at a roller perpendicular to the floor. In order to solve for that reaction at E, here's two unknowns. I come over here and some moments about point A. So moments about A equals 0 is equal to minus 500 newtons multiplied times 16 meters plus the EY force times 16, 26, 28, 36 meters. And that'll let me solve for EY.
222.2.
222.2 newtons. That means I can get this one from some forces Y. In other words, this pressing up plus this pressing up has to equal this pressing down, and therefore this answer is
277.8.
277.8 newtons. Since nobody's pushing on the frame in the horizontal direction, that number happens to be 0. Now then, to get inside of the structure, you actually take the members apart. You actually come over and you draw this member by itself, and you draw this member by itself, and you draw this member by itself. And this member has already been a few things solved. This is 277.8. This is 0. However, by separating these two members, you have opened up a pin, and there is the potential. You'll notice I put an arrowhead on it. You'll notice it's probably wrong. You'll notice I gave it a name. Without that, you're doomed. Since you opened up a pin, there are two potential forces at that point. There's my guess for the arrowhead. His name is B vertical. You opened up the pin at A. There's my guess, A horizontal. Here's my guess, A vertical. And you need dimensions, or you'll go crazy. On the free body, this dimension is 8, and this dimension is 10. And across the structure, this dimension is 8, and that dimension is 10. Alright, now then. Darn, I gave that A really bad name, or that force there, because that's pin C. That ought to be C horizontal and C vertical. We already got an A horizontal and A vertical down here. Alright, now here's important point. If you think someone is pushing up on this member, the only way you can push up on this member is if you'll let somebody put his feet here and push down. You must show that other force, or that force, on the other member in the other direction. If you don't show it in the other direction, the solution will be wrong, and even statics won't tell you it's wrong. It'll just all work out. The reason is if I told you to stand over here and push up on this steel pin, the only way you could do it is if I let you put your feet, and your feet will push down on this one. By the same token, if I tied you to this thing here with a piece of rope and said, put your hands out and pull this member to me, and you pull that member towards you, the only way that can happen is if you pull on this member. And his name is C horizontal. Then here has to be B horizontal And here has to be B vertical. And then on this one, you may look at it and say, well, since he showed this up, he'll be showing this one down. Not so. This one gets shown up. And the reason it gets shown up is because it's the same member. In other words, if EY was guessed up, or even if it is proven to actually go up on this member, and you merely redraw the member like a ditto machine or like a Xerox, you wouldn't expect this arrowhead to flop on the Xerox. You just redrew the member, you redraw the force. Then why do these not match? The reason is because if this goes to the right on this member, it goes the other way on the other member. From then on, it's simply a matter of putting everybody in equilibrium. You have found that this number is 278, pretty close. You have found this number is 0. You have found this number is 222. Now, these can be put in equilibrium by statics. But your sum of your moments equation is always the most powerful equation you've got. If you ever see a horizontal or a vertical member, go towards that first. Because on a horizontal member, a lot of unknowns pass through one point. This one and this one, ooh, and this one too. Whereas on this slanted member, if you sum moments about this point, trying to get rid of these two unknowns, these two rascals here still have moment arms. So go towards a horizontal or a vertical member first. Your equation reads, sum moments about point B equals 0 equals. There's a 500 Newton force. He has an 8 meter moment arm. He is a negative tendency to roll. There's dy. He has a 20 meter moment arm. He is a positive. Solve for dy. 200. So we put 200 once, and we put 200 twice. Put it on that free body as soon as you find it. Now, sum of the forces vertical on this one. If you got 500 down, you got to have 500 up. Got to be 300 here. Got to be 300 here. Now we could try some forces horizontal. That's not going to do us any good. This free body kind of played out. This is to the left. This is to the right. We know they're equal, but we don't know a number for them. It's time to move on. Let's go to a horizontal or a vertical member. Well, so much for that trick. We're going to get stuck going to this one right here. Where should you sum moments? More unknowns pass through this point right here at this time in the solution than any other place. You should sum moments about C. If you sum moments about C, then this is the only unknown you will have right here. And the equation would read, sum moments about C is equal to 0 is equal to, I see a 278. I notice he has an 18 meter moment arm. He also has a negative tendency to roll about point C. I see a 0, fooey on you. I see a 300. He has a 10 meter moment arm. He has a tendency to roll in the positive direction. Finally, I see BX. He has a, here it is over here, a 10 meter moment arm. And he has a positive tendency to roll. And when I solve for BX, I get how much? 200. Now, is that 200 come out a plus number or a minus number?
Plus.
Comes out a plus. All right, that's kind of a shame. It would have been nice had it come out of minus. Had it come out of minus, I'd have been able to show you what I had to do with this arrowhead. I'd have had a list that the answer is 200 twice, and then I would have changed the arrowhead twice, meaning the arrowhead was incorrectly guessed. Now, that's not the case here, but it's just luck that the arrowhead was properly guessed. If the answer is a minus, change the arrowhead to the other end 2 times, just like you listed 2 times. All right. Quickly show you how to set this one up. This is a pin, so I need a reaction at C vertical and a reaction at C horizontal. I need a reaction at A vertical and a reaction at A horizontal. Those are absolute guesses on direction. Half of them are statistically probably going to be in the wrong direction. The equation would read sum moments A equals 0 equals plus RC vertical times 7.5, 8, 9, 10, 11, 12.5 feet minus 500. That's it. Because this guy goes through point A, this guy goes through point A, this guy goes through point A. This guy doesn't have a moment arm because he's already a moment. So you can solve for RC vertical from this equation. Sum forces vertical, solve for RA vertical from this equation. Then you're stuck. These two won't come out. You can sum forces horizontal. You can sum moments till you're blue in the face. Long ago, God decreed 4 unknowns could not be solved by 3 equations. I don't know why. Seemed good at the time. You'll have to break this up into some more free bodies. Here's your free body. You'll put this known number on here. You'll put this unknown number as just a name. You will guess B horizontal. You will guess B vertical. You will put this on there. Then you'll draw a free body of this one. You will put this known number here. You will put this unknown number here. You will put B horizontal the other way on this other member. You will put B vertical this other way on this other member. Since you know this right here, this is the place to go get an answer. Some moments about that point, because he is known. That's your only unknown. Once you list him, you can find him. Once you find him, you can put him there. Once you find him, you can get him by summing moments about this point. It's all downhill from then on. Careful free body is what you need. What does that time say on that thing?
1:03.
An hour and 3 minutes?
Yes.
Oh, that's not bad. That's right on time. All right, I thought we were over. All right, I had one more. Phooey on that. Look at that thing. But let me just mention this, and then we'll quit. If you have a load on member D, E, whatever that is, put it on the member. This 400 goes right on that. This 300 goes right on that. But if you ever have a load right on the joint, you don't care when you're drawing this free body. It doesn't matter to you, because you just take the force times the moment arm. But when you draw this free body, that's this one, and when you draw this free body, you gotta pick a place, just like a contractor. Contractor has to literally go put that 100-pound force on this member, or he's got to put it on that member. It doesn't make any difference. But if you put the 100 on this one, for heaven's sakes, don't also put the 100 on that one. Now what the steel pin does is the steel pin causes a D vertical and here is a D vertical. And then of course here is a D horizontal, and so here is a D horizontal. But that either has to go on this guy or it has to go on that guy once you split him up. That's important. The contractor wouldn't put it on both of them. He couldn't. He either puts it on one or the other. You have to do the same thing. All right. Well, we've covered enough statics to make you dangerous. Maybe even if you've picked up a few points. I know a guy who took this quiz 3 times. Was kind of interesting. He went back. You can do this. You can go look at your quiz. If you do not pass it, see what you did wrong, see where you need to study. It's a good idea. In his case, he thought if he had gone and complained a little, he might have got it, because he was only 2 or 3 points below where it should have been, and he kind of questioned a couple of the grading. I'm not saying you ought to do that, but I'm saying that coming to these sessions and really studying this stuff, it may only take you 2 or 3 points to make the difference between pass and not pass. I guess this is probably a normal distribution curve, you know, and I don't know where the pass rate is. Oh yeah, I forgot to tell you, go down there, thank you. But 2 or 3 points, there's a lot of people in there. You know, it'd be better to be on that side than to be on that side. So I wish you every luck in the world. You can give me a call if you like. I believe Nancy will be getting email addresses from us. I have her email address. Some other information you might find at our website. The website is engineering, engineeringregistration. It seemed like a really good name till we had to type it out a bunch of times. Engineering registration at Texas A&M University .educational. So if you have access to the web, you can go there and find general information on the quiz. There's a bunch of good links to other sources. The people who make out the quiz, we link to them. The state of Texas information, we link to them. We also link to a bunch of publishers who publish very good EIT and fundamentals review manuals. And I will probably see you Wednesday night to go over this information. And